Hello and welcome to Precalculus lesson number 4. In this video, we're going to learn a whole lot about quadratic equations. Any equation that can be put into the form ax squared plus bx plus c equals 0, where a, b, and c belong to the set of complex numbers, and a is not 0, is called a quadratic equation in standard form. Now, why is it important that we make a non-zero? Because think about it, if a is 0, the square term is gone and the equation simply collapses down to a linear form or a linear equation. So bx plus c equals 0. So that's why we have the requirement that the lead coefficient, which is what a is called, because the coefficient of the highest degree term in a equation of this type or expression on the left side of this equation is called the lead coefficient, and we need the lead coefficient to be non-zero in order for this to be considered a quadratic equation. Again, here a, b, and c are complex constants and x is a complex variable. We will now explore different methods for solving quadratic equations. Some of the methods that we're going to study are going to be universal in that they can solve any quadratic equation. Universal, of course, we mean the universe we're considering here is the universe of all quadratic equations. And some of the other methods we'll study are not universal and they will only apply in certain situations, which we will discuss. One of the first methods that were introduced in algebra for solving quadratic equations is the method of factoring. Now, this is not a universal method in that it only works with quadratic equations in standard form whose non-zero side, remember we're talking about this side, this is the non-zero side of the quadratic equation in standard form because the other side is obviously 0. This side should be factorable over the set of integers. So it only works for quadratic equations in standard form whose non-zero side is factorable over z, z being the set of integers. So all the equations that we know how to factor nicely, the quadratic expressions that we know how to solve a factor over the set of integers would work with this method. We're going to look at how that is done. Before we actually solve quadratic equations using the factoring method, it's good to remember what the zero factor property or the ZFP refers to, which basically states that if a product of two numbers is 0, then either the first number is 0 or the second number is 0. Now, the OR used above is an inclusive OR, so that means either A is 0 or B is 0 or both are 0. That's okay too. An exclusive OR between two statements would be one or the other, but not both. But this is not an exclusive OR, and generally speaking in mathematics when we use OR, that is an inclusive OR. Which is different from real life, right? Usually in real life, if you say, I'm going to go to the movies or I'm going to go to the live theater, you don't mean you're going to do both. You mean you're going to do one or the other, but not both. But in mathematics, we use it in the inclusive sense. The essence of the zero factor property is the fact that there's no way you can multiply two numbers and get 0 and neither of those numbers being 0. In other words, if you multiply two numbers and get 0, one or both would have to be 0. And notice that the zero factor property is sometimes referred to as the principle of zero product, so PZP. In case you see that phrase, that refers to the same property. The procedure for solving higher order equations using factoring is a little different from the procedure we use from solving linear equations. Remember that to solve linear equations, we simplify both sides of the equation, then we separate, basically move all the variable terms to one side and simplify, and move all the constant terms to the other side and simplify. then we proceed to solve the equation very simply at that point. The procedure for solving higher order equations using factoring is as follows. We move all the non-zero terms to one side and we get 0 on the other side. Then we simplify and fully factor the non-zero side, and then we apply the theorem or the property we just learned about, the zero factor property, and then we solve any resulting equations that pop up after the application of the zero factor property. It all will make a lot more sense when we see it in action. All right, so let's say we want to solve this equation x squared minus 5x equals -4 using factoring. Now, remember that we're going to move all the terms to one side, get 0 on the other side, correct? So we have x squared minus 5x. Now we have -4, but let me just write the whole equation over again, like that. So we want to move the -4 to the other side. We're going to add 4 to both sides, right? So we end up with x squared minus 5x plus 4 is equal to 0. Now, this business of moving a term from one side to the other is used so often that it would be nice if we had a shortcut where we wouldn't have to show this every time, right? It would save us some time. So that's where the principle of change sides, change signs comes in. So in other words, you can take any term of an equation and move it from one side to the other side, either from the left to the right or from the right to the left, as long as you change the sign of that term. Now, the reason for that is, of course, simple, because you're adding the opposite to each side, right? That's how you're accomplishing the moving or the changing of sides. So from this point forward, we're just going to skip this +4 business and just go from this to this without any confusion, right? So we're changing the side for -4, so when we move it to the other side, it becomes +4, right? And on this side, of course, we're left with 0. All right, so then we go ahead and factor that. So remember here, we can use the big cross. We're looking for two numbers whose product is +4 and whose sum is -5, right? Think of what two numbers can accomplish that. If you think about it, you're going to come up with 4 and 1, right? But since we want the sum to be -5, they're both going to have to be negative, right? So -4 and -1. So this factors as such. Like so. All right. So whenever you factor, you should do a quick three-step check. First times first should be first. This is the FOIL check. Last times last should be last, which it is. And the inner product and the outer product should add up to the middle term. And as you notice here, they do. -4x and -x is -5x. Now we know we've done the factorization correctly. So now we go ahead and apply the zero factor property, right? So we took care of steps 1 and 2. Now we're on step 3. We're going to go ahead and set each factor equal to 0 because we have a product of two factors that's 0. So either this factor is 0 or this factor is 0. So like so. So this one, when we solve, now we're on step 4. We're just solving all the resulting equations. So we get x equals 4 or x equals 1. And when we write our solution set, we're going to write 1 and 4 within braces like that. Of course, remember, sets are not ordered. You could have written 4, 1 within those braces and you would have been just fine, okay? So always a good idea to check your solutions to make sure they indeed work, I will let you do that, because this video is going to be a rather long one already. So for the sake of it not becoming any longer, I'll let you do the checks, but both of those should work. Okay, here we're going to solve another equation, x cubed equals 9x. So we're going to follow the procedure. We'll move we start with x cubed equals 9x. We'll go ahead and move the 9x to the left side. Remember, change sides, change signs. We're basically adding negative 9x to both sides. So we end up with that. Now we're going to go ahead and factor, right? So the first thing we notice is that we can factor out an x from both terms. So we do that. That leaves us x squared minus 9 equals 0. So now we notice that here we have a difference of squares. As we encounter these factoring scenarios, I'll remind you of the rules that we're using. Here we're going to use the difference of squares factoring formula, which says if you have a first square minus a last square, it factors as the first plus the last times the first minus the last. And of course you could write f minus l first and then f plus l. That's no problem either way. So we get x times, now here your L is going to be 3, right? Because it's 3 that you square to get 9. So x plus 3 times x minus 3. In case it's been a while since you did algebra, I can show you it's x squared minus 3 squared, right? So notice f is the role of f is being played by x, the role of L is being played by 3. That's why you get x plus 3 times x minus 3. So now we apply the zero factor property by setting each of these factors. Remember, x by itself is a factor, x plus 3 is a factor, and x minus 3 is a factor. So now we say either x is 0 or x plus 3 equals 0. Now here we're doing a little bit of cheating, because in mathematics a comma usually means and. But here we're actually just using it as a separator. It's playing the role of an or in reality, but we know what we're dealing with, so that's okay. Like so, this is just for the purpose of separating these equations. So the first one, there's nothing to do, it's already solved. For the second one, we get x equals, remember we're going to move the positive 3 to the other side, becomes negative 3, so x equals negative 3. And for this one, we'll move the negative 3 to the other side, so we get x equals 3. So there are 3 solutions. We're going to write S equals the set containing 0, negative 3, or 3. Now, I didn't put those in any particular order because order does not matter when it comes to sets, okay? So there you go. Now, sometimes people choose to put them, like say, in ascending order, just so that they become a little bit easier to check, like negative 3, 0, 3. But remember, these two sets are exactly the same. This one has no advantage over that one, except the short advantage of you being able to verify what the numbers are very quickly. Otherwise, they're equal as far as mathematics is concerned. All right. As with all problems that we do, always make sure that you initially try to do it on your own without getting any help. If you can't do it, then you can watch me kind of go through it. As you watch me do it, you may need only 1 or 2 steps to realize, oh, okay, I got the rest, right? Well, at that point, pause the video and finish it. But if you really don't know what's going on, and even if you watch me do all of it, it's okay. Then get a blank piece of paper or go to a blank, document in your iPad or whatever, and just write the problem down, redo it without getting any kind of help. And keep repeating that procedure until you can, in fact, do it with no help. At that point, you can move on to the next problem. And you'll do that with every problem that we do if you really want to make progress. And you'll see it makes a real difference when you're really engaged in the problem solving process. Okay, next we want to learn how to solve equations using the square root property. This is not a universal method in the sense that it only works for quadratic equations that can be put into these particular forms, right? One of them is x squared equals some constant. The other one is the more general form, the square of a binomial ax plus b is equal to a constant. And if it's in either one of these two forms, then we'll be able to use what's called the square root property. So we'll go ahead and take a look at that next. All right, let's take a look at an equation first to give us a motivation for where the square root property comes from. Let's say I want to solve this equation, x squared equals 7, right? Well, I know that I can think of 7 as the square root of 7, right? So then I have x squared minus quantity square root of 7 squared equals 0. Now, if you recall the formula we just used, f squared minus l squared equals f plus l times f minus l. Remember that these two expressions are called conjugates of one another. So we say that a difference of squares factors as the product of conjugates, okay? So here we end up with x minus square root of 7 times x plus square root of 7 equals 0. And then we apply the zero factor property, so we get x is either square root of 7 or x is equal to negative square root of 7 once we solve those two simple linear equations. Now, because we encounter this type of problem very frequently in mathematics and related disciplines, it would be nice to get to these solutions much more quickly. And so we're going to generalize this type of equation in the following theorem. And the theorem is the square root property, which says if x squared equals k, then x is plus or minus square root of k. That's all there is to it. But you see, here I reproduced the steps that we used to solve this equation in our previous screen. And look how almost identical it is to the general case with k, right? All we do is wherever we see 7, we replace it with what? With k, and by the end of that, we have established the square root property. Remember, when you have either x equals negative square root of k or positive square root of k, we can write that in this compact form as x equals plus or minus square root of k. Now, that's actually positive or negative, because when you use those as signs rather than operations, we usually say positive or negative, but you have to admit plus or minus rolls off the tongue much better, right? That's why we use plus or minus. All right, but so whenever you see this kind of notation, that's actually two solutions you're looking at. In this compact form, they are being written so that we can save some space and time. Otherwise, you're looking at two solutions. So here's the square root property. If x squared equals k, then x equals plus or minus square root of k. Now, there's a generalized version of the square root property, which can also be proven very easily. And the fact is that if quantity ax plus b squared equals k, notice that instead of saying open parentheses ax plus b close parentheses and then square, etc., if you just say quantity, that means the moment somebody hears quantity, that means in their mind they're going to open parentheses. And the moment you say an operation such as squared, that's when they know they should close the parentheses and square. So it's much easier than saying open parentheses ax plus b close parentheses squared, right? So we just say quantity ax plus b squared. Now, why do we even have to do that? Why can't we just say ax plus b squared? Because if you just say ax plus b squared and somebody is listening to you, they should be interpreting that as ax plus b squared, such as that. So the only thing that would get squared in that scenario would be the b. That's why you need to say either open parentheses ax plus b close parentheses squared, or much better and much more professionally sounding, you can just say quantity ax plus b squared. That way we know that all of ax plus b is being squared, not just the what? Not just the b part. So if quantity ax plus b squared is k, then ax plus b is going to have to be what? Positive or negative square root of k. All of these make a lot of sense, right? Think about it. Think of it with something familiar. Let's say x squared is 16, right? What can x possibly be? Well, remember, there are only two numbers that you can square to get 16, right? One of them is 4, the other one is what? Negative 4. So you say x equals plus or minus square root of 16, and that will give you the same two results that you intuitively knew should work anyway, right? So it's a very, very intuitive result. So we get x equals plus or minus 4. All right. So let's go ahead and take a look at some problems now. All right, so here we're going to solve by using the square root property. So we have x squared equals 144. We are in the form of x squared equals some constant. Therefore, we're going to apply that by the square root property. We know that x should be plus or minus square root of k, right? Now you get x equals plus or minus square root of 144. So we know that that should be 12, right? So we get x equals plus or minus 12. So when you write your solution set, you're either going to write negative 12 comma 12 or 12 comma negative 12, doesn't make any difference. Or you can write just plus or minus 12 like this, right? So both of those should be acceptable solutions, okay? All right, so here we want to solve. As always, remember, always try everything on your own first, then come and watch what I do. Okay, so we have u squared equals 24. Now we are in the proper format. If we have something squared equals a constant, then that some number must be plus or minus the square root of the constant, right? So here, instead of x, we have u, makes no difference, right? You can replace x and u. That's just called a dummy variable. So we get u equals plus or minus square root of 24. Now, if we take a look at the prime factorization of 24, we know that we start with prime numbers that go into 24. The smallest one is 2. 2 goes into 24 12 times. We write it there below the 24. Again, 2 will go into 12 6 times. And then 2 will go into 6 3 times. And 3 goes into 3 itself 1 time. So at each step, ask yourself, what's the smallest prime number that goes into the number on the right? Write it right there on its left, divide, and write the result below the original number. Again, what's the smallest number that goes into 12? 2. Go ahead and divide, write the result here. Smallest prime that goes into 6 is 2, divide, you get 3. Smallest prime that goes into 3, well, because 3 is a prime number, the smallest prime number that goes into a prime number is, of course, itself. And you get 1. Once you get to the 1, you're finished. All right, so you can see on the left here, you have the prime factorization of 24. So you can see there is a perfect square that's hidden inside 24, right? So we can write this as plus or minus square root of 2 squared times the square root of 2 times 3. See? Now notice that's 2 times, well, here if you could do it, you may want to do it in 2 steps so it makes more sense to you. So you can write it as plus or minus square root of 2 squared times 2 times 3. Then you can split up the perfect square part and the non-perfect square part. See? Now what is the square root of 2 squared? What number do you square to get 2 squared? Of course, that's just 2, right? Radical 6, right? So there's the solution right there in simplified form. You always want to simplify. So we write the solution set as the set containing positive or negative or plus or minus 2 radical 6, like so. All right, and if you want to do a quick check, just look, just take 2 radical 6, right? Well, you can actually take either one and square it. Since we're squaring, the signs are both going to end up being positive, right? Now, 2 squared is 4, and what is square root of 6 squared? That's just 6. What's 4 times 6? 24. So when I square either positive or negative 2 radical 6, I end up with 24, so therefore those are indeed solutions of this equation. All right, here's another problem we're going to solve by the square root property. Notice that we would be able to solve this by factoring as well, right? Just factor as a difference of squares and solve by the zero factor property. But this time we want to get practice with the square root property, so we're going to solve this using the square root property. So first we need to put it in the proper format, which is x squared equals some constant, right? So we have 9x squared equals 25. So x squared equals 25 over 9. So now we go ahead and we have the right format now. Now we're in the proper format, so we can go ahead and apply the square root property. So I can say, therefore, by the square root property, x equals plus or minus square root of 25 over 9, which of course is plus or minus 5/3, right? So we write the solution set as the set containing plus or minus 5/3, like so. All right. So again, make sure you know how to do each of these problems completely on your own before you proceed. All right. So here we're solving this equation by the square root property. So we have x squared plus 28 equals 0. Give it a try on your own. Okay, welcome back. So x squared equals negative 28, right? Change sides, change signs, right? I move 28 to the other side by subtracting 28 from both sides, right? That's how I end up with x squared equals negative 28. Now I'm in the right format. I have x squared equals some number, therefore x is what? Plus or minus the square root of that number. If you remember, we never said k has to be positive or non-negative or anything like that, did we? We did not. So we get x equals plus or minus square root of negative 28. Now from our section that dealt with complex numbers, we learned how to simplify that. Remember, we break it up into 3 parts. In the last one, we throw in the negative 1. In these two, we put the perfect square part and the non-perfect square part. So 28, again, we have 2, 14, 2, 7, 7, 1. So there's the perfect square part, 2 squared. The non-perfect square part of 28 as a factorization is 7. And then you have the negative 1. So we get plus or minus. Now the square root of 2 squared is of course just 2 radical 7. And then instead of square root of negative 1, just put I. That is considered to be the simplest form of square root of negative 1, I. So now we can write our solution set. So we get positive or negative 2 radical 7, I, like so. Okay, now try this one before you come back. Okay, so we have quantity x plus 3 squared equals 144. Remember, we did have a generalized version of the square root property that said if ax, quantity ax plus b squared equals k, that implies ax plus b must be plus or minus square root of k. So we're going to apply, so we are ready to apply this generalized version of the square root property. So we get x plus 3 equals plus or minus square root of 144. So we get x is equal to negative 3 plus or minus 12, right? So I moved the 3 to the other side, it became negative 3, and here I'm just simplifying the square root of 144, right? So now we're going to have the positive case and the negative case. The plus case gives me negative 3 plus 12, which is 9. The minus case will give us x equals negative 3 minus 12, so we get x equals what? Negative 15. So when it's kind of like nice numbers, whole numbers, or integers like these, make sure that you figure out each one, what each one gives you, and simplify. So you don't want to put this into your solution set when it can be reduced and simplified further, okay? So now we put the solution set contains negative 15 and 9, like so. Separate your solutions with a comma when you have more than one solution. All right, so there is that. And of course, a quick check will show you these are correct. Negative 15 plus 3, that's negative 12. What's the square of negative 12? 144. 9 plus 3 is 12. What's the square of 12? 144. So we're good to go. Here's another one for you to try. Go ahead and try it, see what you get, then come back. All right, so quantity 2x minus 3 squared equals negative 24. We are in the form of quantity ax plus b squared equals k. Therefore, ax plus b must be plus or minus square root of k. So we end up with 2x minus 3 equals plus or minus square root of 24, sorry. So 2x minus 3 equals plus or minus square root of negative 24. Be very careful. So now we get 2x equals 3 plus or minus square root of negative 24. Let's go ahead and simplify that. 24, 2 gives me 12, 2 gives me 6, 2 gives me 3, 3 gives me 1. We already did this. So it's this, so we can basically say 2x equals 3 plus or minus square root of 4 times the square root of 6 times the square root of negative 1, right? So we get 2x equals 3 plus or minus 2 radical 6 I, correct? Instead of the square root of negative 1, we'll always write I. So now we're ready to solve for x. That's 2x. We want x. So we divide both sides by 2. So we get x equals 3 plus or minus 2 radical 6i over 2. Now, we could leave it like that, but it's better if you go ahead and split them up. So we get 3 halves plus or minus 2 radical 6 over 2i. Notice that these 2's cancel out. So we end up with x equals 3 halves plus or minus square root of 6i. Let me go ahead and erase this factorization so I can now write my solution set. So for the solution set, we go ahead and put 3 halves plus or minus square root of 6i, or we can list them separately. So we can say 3 halves plus square root of 6i, comma, 3 halves minus square root of 6i, and that's it. Okay? So that's how you would handle that one. Now next, we're going to go to a more general situation and learn how to solve quadratic equation by what's called the completing the square. And this is a universal method. That means it can be used to solve any quadratic equation. Let's see how we will take care of that. All right, before we can solve a quadratic equation using the method of completing the square, we have to learn what completing the square is, right? So I want you to consider this expression, the square of x plus 3, or quantity x plus 3 squared. Notice that that just means quantity x plus 3 times quantity x plus 3. Then we go ahead and square and distribute the x to get x squared plus 3x, and then we distribute the 3 to get 3x plus 9, right? So we end up with combining these two middle terms, we get x squared plus 6x plus 9. Now, given an expression like x squared plus 6x, it would be very helpful to be able to find the constant that needs to be added to x squared plus 6x to make a perfect square trinomial. Now, from what we've seen up here, we obviously know that constant needs to be 9, right? But what if we didn't have the work that's shown above, right? In fact, what if we were asked to find the constant that we must add to, for example, x squared plus 10x to transform it into a perfect square trinomial? Can we find it? In other words, is there enough information hidden inside x squared plus 10x to help us find that constant? And the answer, as long as the coefficient of the square term, meaning the coefficient of the x squared term, right, is 1, is a resounding yes. But remember, that coefficient needs to be 1 for what we're about to do to work. Now, to understand this better, why we're going to do what we're going to do with these steps, consider this. Let's generalize. Instead of just looking at x plus some constant, let's just say x plus some number, right? And we want to square that, the square of x plus n. You notice it's the same procedure as we did up here. So distribute the x, when finished, distribute the n. So we get x squared plus nx plus nx plus n squared. So it's called sequential distribution, basically. And then these two combine to give us 2nx, and we have n squared at the end. So now if I look at x squared plus 2nx, right? Is there any way I can come up with that last term if I didn't know it? Well, think about it. Very simple, right? Take that 2n and take 1/2 of it. In other words, divide it by 2 or multiply it by 1/2, and what do you get? What's 1/2 times 2n? That's n, right? Now all you got to do to get this last term is to square it. So square the number you found in step. So two-step process for completing the square. If you know the square term and the x term of a trinomial, then you can get the constant term or the last term of the trinomial by going through these two steps. First, find 1/2 the coefficient of the x term or the first degree term, and then step 2, square it, and that's going to be the number you need to add to complete the square. So let's see this in action. It becomes real easy after a couple of tries, okay? I want to reiterate, because it's extremely important to note that the process only works if the coefficient of the x squared term is 1, or the lead coefficient. We will learn how to deal with situations where the coefficient is not 1 while we're solving equations using the method of completing the square. So let's say we want to go ahead and try the x squared plus 10x, which we mentioned in the last step, right? So remember, very simple, right? 2 steps. Step 1, take 1/2 the coefficient of x. What's the coefficient of x? 10. So 1/2 of 10, and that's what? Yes, I agree, it's 5. Now for step 2, just take the 5 and square it. You get what? 25. So I just realized this. I realized that if I take x squared plus 10x and I add 25 to it, I have created a perfect square trinomial. And how is that going to factor? Easy. X plus, here's a tip for you, whatever the result of the step 1 was, and then square, okay? If that's positive, this is going to be positive. If that's negative, that's going to be a minus, okay? So quantity x plus 5 squared is what we just created. So this is what we mean by completing the square. Now, we're not dealing with equations right now, so we're only adding the 25 without worrying about what happens. But when we're dealing with an equation, we got to keep the balance, right? So if we add a 25 here, we'll have to add it on the other side of the equation, etc. So we'll get to that soon. So go ahead and try that and see what you get for the completing of the square on this particular binomial. Turn this binomial into a perfect square trinomial is what you're trying to do, okay? A binomial is basically a polynomial with 2 terms. A trinomial is a polynomial with 3 terms. So we're going to take a binomial and transform it into not just any trinomial, but a perfect square trinomial. All right, so again, I'm sure you did this already. For the first step, we take 1/2 the coefficient of the first degree term, or the y term, right, in this case, right? -7. So what is that? That's just -7/2, right? For step 2, take what you found in step 1 and square it. So what is quantity -7/2 squared? Well, that's going to be 49. Touchy screen. 49 over 4, right? So that tells us that if we take y squared minus 7y and we add 49 over 4 to it, we've created a perfect square trinomial, and we can find out what goes in here very easily. Y, of course, is just going to be y, the first term. For the second term, you have to look no further than the result of your first step. So -7/2, right? Try it. Try multiplying those. Y minus 7/2 times y minus 7/2, right? That's y squared minus 7/2y. I'm just multiplying it like a times table, right? Minus 7/2y plus 49 over 4. That's -7/2 times -7/2. Now these two, right, they combine to give me -14 over 2y, which is just -7y, right? So I get y squared minus 7y plus 49 over 4, which is exactly what we had here, okay? So that's how you complete the square with some fractions involved. Okay, so you should be able to do this one now. Try it. All right, so remember, first step. Now, in each step, we have to make sure we check to see if the coefficient is 1. Here it was 1. Notice in the last one, the coefficient was 1. In this one, the coefficient of the square term is 1. So that's the only time we can proceed, okay? We'll see what happens if it's not later, but we deal with that in equation form, okay? So here, step 1, go ahead and take 1/2 of the coefficient of the first degree term, so t. So 3/5, right? Now, what is 1/2 of 3/5? Well, that's just 3/10, right? So step 2, you're going to take the 3/10 and you're going to square it. So take half the coefficient of the first degree term, and then in the second step, square that to get 9 over 100. So now I know that if I take t squared plus 3/5 t and I add 9 over 100 to it, I've created a perfect square trinomial. So what is the binomial that if I square, I get this trinomial where it's going to be t plus whatever you have to square to get that, which we know it was what? 3/10. There it is. So that's how you complete the square on that. Okay, now we have enough knowledge to go ahead and start solving quadratic equations by completing the square. We will outline the steps required through an example. Note that this is a universal method that can be used to solve any quadratic equation. that can be put into this standard form, right? All right, let's go ahead and proceed. Here I put R, but you can also replace that with C, the general notion being that it works for complex coefficients as well. All right, so let's say we want to solve x squared plus 10x minus 24 equals 0 by completing the square. So here's what we're going to do. We're going to get the two variable terms on one side, and we're going to move the constant term to the other side, okay? So we have x squared plus 10x equals, remember we changed sides for negative 24, so it became positive 24, right? Change sides, change signs. Why? Because we're just adding the opposite to both sides. Now we're going to complete the square on the left side, right? Or it doesn't matter, if this were on the right, you would complete the square on that side. So whichever side the variable terms are, right? So remember, we're going to take 1/2 of the coefficient of x, which is 10, and we get 5, and we square that to get what? 25. Now we're going to add the 25 to x squared plus 10x to complete the square on that side, right? But now we're dealing with an equation, so we can't just do something to one side of an equation. Whatever we do there, we have to do to the other side as well. So we need to add the 25 to the 24 that's already on the other side, right? So we end up with x squared plus 10x plus 25 equals 49. Now this, as you recall, is the square of this binomial, x plus 5, right? So we get quantity x plus 5 squared equals 49. Well, that's very convenient because now we're in the form that we know how to deal with. Now we can apply the square root property and say, oh, since the square of x plus 5 is 49, that means x plus 5 must be what? Plus or minus the square root of 49. So we get x plus 5 equals plus or minus 7. So x equals -5. I'm just moving the 5 to the other side, becomes -5 plus or minus 7, right? Remember, now we're going to split into two parts. These are nice numbers. We should find out what the plus and the minus cases give us, right? So the plus case gives us -5 plus 7, or 2. The minus case gives us -5 minus 7, which is -12. Then we just write the solution set, okay? Take a look at the steps. That's exactly what you're going to do every time you want to solve by completing the square. So very easy. The only difference being, if this coefficient happens not to be 1, we go ahead and just divide off whatever it is other than 1 to get 1. That's it. That's the only complication that come in. Otherwise, very easy. Make sure you can handle all of those steps completely on your own without any help before you proceed. All right, so here we have a equation with, several fractions in it. So before we do anything with this equation, we're going to transform it into an equivalent equation with no fractions, because it'll be much easier to work with whole numbers or integers. So just find the LCD of all the denominators, which is what? In this case, between 2, 3, and 4 would be 12, right? So now we go ahead and multiply both sides of that equation by 12. So, and remember that we're going to end up distributing, right? Because there are 3 terms on this side. So when I multiply this side by 12, I have to distribute. So I get 12 times each of those terms equals 12 times 0, right? So 12 times 1/2 x squared plus 12 times 1/3 x plus 12 times 1/4 equals 12 times 0. And of course we have to multiply 12 on both sides. If a equals b, that implies a times c equals b times c. That's the multiplication property of equality, right? So on the first one, I noticed 2 and 12 leave me 6. In the second term, 3 and 12 leave us 4 on top. In the third term, 4 and 12 leave us 3 on the top. So now we end up with 6x squared plus 4x plus 3 equals 0, right? So this is the step you really want to be making sure you're not leaving anything behind and you're doing all of this correctly, okay? All this canceling, all right? So we have 6x squared plus 4x plus 3 equals 0. So now we go ahead and proceed by doing what we've always do. Go ahead and get the square term and the x term on one side and move the constant to the other side. All right, now I noticed that if I want to proceed with completing the square, I'm going to run into a little issue because completing the square method, as I've learned it, only works if the coefficient of the x squared term is 1, but here I have a 6, right? So no problem. We'll go ahead and divide the 6 off at this point. So we go ahead and divide both terms, both sides of the equation by 6, and we get, now remember, this is going to split up like this: 6x squared over 6 plus 4x over 6 equals negative 3 over 6. So we end up with x squared plus 2/3 x equals negative 1/2, correct? All right, here we just cross cancel the 4 and the 6. 2 goes into both of them, so we get 2/3. So now we're ready to complete the square because we're in the proper form, right? We have a 1 for the coefficient of x squared, so we can proceed. Step 1, we take 1/2 of the coefficient of x, which is 2/3. Notice the 2's will cancel out, so we end up with 1/3. For step 2, we take that 1/3 we obtained in step 1 and square it to get 1/9. So I know that I need to add 1/9 on the left side to complete the square. But because this is an equation, I also have to add the 1/9 on the right side, like so. Okay? Now, the left side is now a perfect square trinomial. What is it a perfect square of? Well, we know it's the perfect square of x and then plus whatever this was, which was 1/3, right? Or just think about it. If this sign is, if the signs are all positive, then that's going to be a plus. If this is a minus, then this is going to be a minus. And what goes in here, whatever you have to square to get this number. So if you don't want to look at what the step 1 resulted, you can just look here. What do I square to get 1/9? 1/3. So on this side, on the other side, we need to go ahead and find the common denominator, which is 18. So I need to multiply the 2 by 9 to get 18, which means I'll have to do the same to the 1 on top. On the next one, I need to multiply the 9 by 2, so we have to do the same on the top. So we end up with negative 9 plus 2, which is what? What's negative 9 plus 2? That's negative 7, right? Over 18. Okay? So on this side, remember, it's quantity x plus 1/3 squared. Don't put, we need to put the 2 for the exponent. So we have quantity x plus 1/3 squared equals negative 7 over 18. Now we're ready to apply the square root property. So we get x plus 1/3 equals plus or minus square root of negative 7 over 18, correct? So we get x equals, I'm going to move the 1/3 to the other side, becomes negative 1/3 plus or minus. Now let's do this. Let's write that as the square root of 7 over the square root of 18, which I'll go ahead and write as 2 times 9. And then don't forget, we're going to have a square root of negative 1 as well, because we're going to split up this radical in that way, right? And we end up with negative 1/3. You can watch the section we did on complex numbers for help with this if you've forgotten it. Notice that I can split up this radical as down below as the square root of 9 times the square root of 2, and then we have just simply an I on the outside right there. So we end up with, don't forget the plus or minus in between. So we get negative 1/3 plus or minus square root of 7 over 3 radical 2. Don't forget that we need to rationalize that denominator. We can do that by just multiplying top and bottom by radical 2 now, right? So let me continue over here. So we get x equals negative 1/3 plus or minus, that's going to be square root of 14, right? And down below we have a 3, and then radical 2 times radical 2 is going to give us 2 times 3, which is 6. And don't forget the I, okay? There you go. So here, let me save one step. So I'm just going to say, instead of that, I'm going to say the solution set is the set containing those two numbers, those two complex conjugates, right? Negative 1/3 plus square root of 14 over 6i, and negative 1/3 minus square root of 14 over 6i. So that's how you would handle a problem like that. Remember, it looks a little bit trickier and scarier, but it's not. Once you run through it a few times, it's all about familiarity, right? So the more it scares you, the more you should practice it. Then the fear completely goes away because it just becomes second nature to you. Nobody, is born and starts doing this stuff with no problem. Everybody has to go through the phase of acclimation and practice with these till they get comfortable with them, okay? So make sure you practice them and you're comfortable before you proceed. All right, next we'll look at another universal method very closely related to the method of solving by completing the square, called using the quadratic formula. It's again a universal method that can be used to solve any quadratic equation. Now, we have already learned how to solve any quadratic equation with complex coefficients by completing the square. We will now solve a general quadratic equation using the method of completing the square, and that will help us find the formula with which we can solve any quadratic equation while bypassing the steps involved in the completing the square process. We will call this formula the quadratic formula. In essence, the quadratic formula is just a shortcut for the method of completing the square. Note that, just as in the case of solving a quadratic equation by completing the square, solving a quadratic equation using the quadratic formula is a universal method, and it can solve any quadratic equation for us as long as it can be put into this standard form, right? And let's go ahead and take a look at how it works. Now, here I'm going to solve two equations side by side, okay, for you. On the left side, I'll solve this equation by the method of completing the square. And on this side, I'm going to solve the very general equation ax squared plus bx plus c equals 0 using the same method of completing the square. So here, what would we do? We would take 2x squared plus 3x and set it equal to -1, right? In other words, move the constant to the other side. But guess what? We'll do exactly the same thing here. Ax squared plus bx equals -c. Then we would go ahead and make sure that the lead coefficient is 1 by dividing both sides by 2, right? And that's exactly what we will do over here, but instead of 2, we divide by what? By a, right? So we end up with this equation. Next, we would do what? We would take the 1/2, the coefficient of, let me show you a little bit of detail here. So here, the coefficient of the x term is 3/2, right? So we would have 1/2 of 3/2, which is what? 3/4, and then we would go ahead and square the 3/4 to get what? 9/16, right? That's why we're adding 3/4 squared to both sides, which is 9/16. Now this turns into this binomial square of a binomial, right? Because this is a perfect square trinomial. It's the perfect square of x plus 3/4. Over here, the exact same thing. It's going to be the perfect square of x plus b over 2a, right? On the left side, and on the right side, we just go ahead and combine like that. So here, notice I wrote this one first because it's going to be a little bit easier to go to the next step, and I put the minus c over a on as the second term. No problem, we can always do that by the commutative property of addition. Okay, so now we just simplify, right? We combine these two terms. Notice that you have to multiply the 2 by 8 and the 1 by 8, so you get negative 8 plus 9, which is positive 1, right? That's where this comes from. And over here, we need to go ahead and get a common denominator, which is 4a squared. So that means we have to multiply the a by 4a. So we have to do the same on the top, right? So notice that's how we end up with b squared minus 4ac over 4a squared, because both denominators are now 4a squared, right? So then we do what? Then we apply the square root property. So we get x plus 3/4 equals plus or minus square root of 1/16 over here. And over here, same way, we go x plus b over 2a equals plus or minus square root of this expression, like that. So here we notice that we can simplify further. We can write this as plus or minus square root of 1 over 4, right? Same here. We can say that we can split this up, square root of b squared minus 4ac over the square root of 4a squared. What do you need to square to get 4a squared? In other words, what squared gives you 4a squared? If you think about it, that has to be what? 2a. Because what happens when you square 2a? You get 4a squared, right? So therefore, we get negative b plus or minus b squared, square root of b squared minus 4ac over 2a, and that's it. There are your two solutions. So we just showed that if ax squared plus bx plus c equals 0, then x must be what? Negative b plus or minus square root of b squared minus 4ac over 2a. We just did what's called derive, not drive as in drive in a car, right? A derivation of a formula is kind of a proof for why the formula works, okay? So when you see derive, it's another way of saying, hey, look, prove that if this is true, then this must be true, right? That's what we mean by deriving the quadratic formula. So this, in essence, is a proof for why the quadratic formula works every time, okay? So here, again, we just simplified. We know how to do this. We've already done it before. So this was what our goal was. So now we can state the quadratic formula officially. So here's the quadratic formula. If ax squared plus bx plus c equals 0, then x equals negative b plus or minus square root of b squared minus 4ac all over 2a. And now notice, how did we come up with the quadratic formula? By using the method of completing, solving a quadratic equation by completing the square. That's what I meant when I said this is just a shortcut. So it helps you bypass all those steps and just get to the answer, right? We do it once for general coefficients, and we have a formula that will help us solve any quadratic equation. Okay, so let's go ahead and solve this equation using the quadratic formula. Remember, this equation is not quite ready to be solved using the quadratic formula first. We have to put it in the proper form, which is ax squared plus bx plus c equals 0, right? So we're going to move the negative 2x squared to the other side. It means by adding 2x squared to both sides. So change sides, change signs. It becomes positive 2x squared plus 2x minus 7 equals 0. Now, here's one thing I want you to always watch out for. Notice if you have any common factors that can be divided off. Not factored out. You don't want to have to waste time factoring when there is an equation, because you can just divide it off. Because if there is a common factor other than 1 is of course always a common factor, right? And you divide it off, then the numbers become much smaller and much easier to work with, okay? So go ahead and divide both sides by that common factor if there is one other than 1, but here we don't have one, right? The common factor for 2, 2, and -7 is just 1. So we go ahead and proceed. Now here I want you to be very careful and always write down what A, B, and C are. Here A is 2, B is 2, C is -7. In other words, don't rush into plugging into the quadratic formula. That's how people miss problems, okay? So now we're going to do this. We're going to say, okay, X is going to be, now notice what I'm going to do. I'm not going to rush and write stuff. I'm going to write the actual formula down. -b plus or minus square root of b squared minus 4ac over 2a. One benefit is I'll remember it very quickly if I keep writing it. The second benefit is I'm going to plug in more carefully now, okay? -b, so that means the opposite of b, right? b is 2, so what's the opposite of 2? -2. Plus or minus square root of b squared, that's just going to be 2 squared, which is 4, minus 4 times 2 times c, which is -7. So 4 times a, which was 2, times c, which was -7. Notice I'm not skipping any steps. Over 2 times a, which is 2. So we get -2 plus or minus square root of 4. Now, this negative times that negative, they're going to result in a positive, and 8 times 7 is 56. So 4 plus 56 over 4, right? Now, notice that that's going to become -2 plus or minus square root of 60 over 4. Now, 60, if I find the prime factorization, 2 gives me 30, 2 gives me 15, 3 gives me 5, and 5 gives me 1. So I have a perfect square hidden inside 60. So I'm going to write this as -2 plus or minus square root of the 4 and then square root of 15, right? I can write 4 or 2 squared, it makes no difference. So I get -2 plus or minus, now the square root of 4 is just 2, radical 15 over 4. I noticed that there's a common factor of 2 in all 3 of those, so it's a good idea to factor it out. That leaves me -1 plus or minus square root of 15, but I'm factoring out a 2 over 4. Now I can go ahead and cross cancel the 2 and the 4 to leave me a 2 down below. So now I know what my solutions are. My solutions are x equals -1/2 plus or minus square root of 15 over 2. And if you want to write your solution set, you would just put that, or you could split them up. You could say 1/2 plus square root of 15 over 2, comma, -1/2 minus square root of 15 over 2, like so. Okay? And that's how you handle that using the quadratic formula. Alright, so here's another problem we want to solve using the quadratic formula. So I'll give you the hint that is not ready, obviously. Go ahead and see if you can put it in ax squared plus bx plus c equals 0 form, and then apply the quadratic formula. Then come and see if our answers agree. Alright, so I'm going to go ahead and multiply the 2x plus 1 and the x minus 3 in my favorite method, using my favorite method, which is the table method. So I get 2x squared minus 6x positive x minus 3. Those combine. So I get 2x squared minus 5x minus 3. See how nice and easy that is? Okay. So I have x minus 12 equals 2x squared minus 5x minus 3. All right, now I notice that I have a positive 2x squared on the right side. I'm going to leave that where it is. So let's go ahead and just move everything to the right side and leave a 0 on this side. So we have 2x squared minus 5x minus 3. Bring the x over from the left to the right, it becomes minus x. Bring the negative 12 over to the right, becomes plus 12. Remember, change sides, change signs, okay? Always. All right, so we have 0 is equal to 2x squared minus 6x. I'm combining the negative 5x and the negative x, and then plus 9, right? Negative 3 plus 12, that's 9. So I look for a common factor other than 1. I don't have 1. The common factor between 2, 6, and 9 is just 1. So we go ahead and proceed. Remember, it doesn't matter if you have 0 equals or this equals 0. Same thing, you can apply the quadratic formula. We have a equals 2, b equals negative 6, and c equals 9, right? So we go ahead and say x equals, remember, write the quadratic formula down first. I'm giving you the method that's going to leave the lowest chance that you'll make any errors, okay? Minus 4ac all over 2a. Now substitute carefully. So b is negative 6, so the opposite of b is going to be the opposite of negative 6, which is 6. Now b squared, now what happens when you square negative 6? You get what? You get positive 36, right? Let's go ahead and write that. And then minus 4 times a, which is what? 2 times c, which is what? 9. All over 2 times a, which is 2. So we end up with 6 plus or minus square root of, that's going to be, let me, be safe and just go ahead and use my calculator. Even though you can do that with hand, it's better to do it and be safe, and also because we need to save some time here. So here, otherwise it's 72. 36 minus 72 is negative 36, right? But I want you to always just be safe and not miss points for simple calculations. Right? There you go. So just as we thought, it's negative 36. And then all over 4, right? So we get 6. So we get x equals 6 plus or minus. Of course, 36 is a perfect square, so we can just write square root of 36 times square root of negative 1, right? All over 4. So that's going to be 6 plus or minus 6i over 4. If we break it up or factor out, notice 3 terms here. What's the common factor? 2, right? So if we factor out a 2 on the top, we get 2 times 3 plus or minus 3i over 4. Now I can go ahead and cross cancel legally the 2 and the 4 to leave me a 2. So I get 3 halves plus or minus 3 halves I. Okay? So those are my 2 solutions. I'll let you put them in a solution set form. I could have also done this. Okay? I could have just said 6/4 plus or minus 6/4 I, and then just cross cancel. 2 goes into 6, 3 into 4, 2. Again, 3, 2. So again, you would end up with what? With the same result. Okay? So that's how you would handle that one. Make sure you go into the right form before you apply the quadratic formula. Okay, here we have an equation which you may be thinking, oh, I know how to solve this one, right? That's just x cubed equals -8. And what number do I have to cube to get -8? Well, that would be -2. And you would be totally correct if we were still limited only to the set of real numbers for our solutions. And in fact, -2 is the only real number solution of this equation, or this equation, which is equivalent to it. However, our universe has expanded and we now have access to complex numbers. This equation here will actually have two other solutions that happen to be non-real complex numbers. So let's go ahead and see how that works out. I'm going to go ahead and erase these, and we'll go ahead and we'll use factoring and then the quadratic formula to get to our other solutions. So now, if you recall from algebra, we have a formula for a sum of cubes, which is f cubed plus L cubed equals quantity f plus L times quantity f squared minus fl plus L squared. And there's a negative version as well for the subtraction. F cubed minus L cubed, that's equal to quantity f minus L times quantity f squared plus fl plus L squared. So I'm reminding you that in case you have to use that on the homework or something like that, you have access to both of them. So we can go ahead and factor x cubed plus 8. Notice here f will be x and L will be 2, right? What number do you cube to get 8? 2, right? So L here would be 2. So we get x plus 2, that's f plus L, times x squared minus 2x plus 4, right? What's 2 squared? That's 4, okay? Equals 0. So if I go ahead and apply the zero factor property now, I get either x plus 2 is 0 or x squared minus 2x plus 4 equals 0, right? So this x is going to be -2. That one is already finished. So this one, it looks like it might be a very simple factorable one. Go ahead and try it. You're going to find out that it doesn't factor easily. But that doesn't mean that it's not factorable anymore. It did when we were only dealing with real numbers. But now we can actually solve using the quadratic formula. So a is 1. B is -2 and C is 4, right? Or we could use what? The method of completing the square, either one. They're both universal methods. So we get x equals -b plus or minus square root of b squared minus 4ac over 2a. So we get the opposite of b. B is -2, so the opposite of b is +2. Plus or minus square root of, what's the square of -2? Remember, the whole thing is being squared, so you get 4 minus 4 times a, which is 1, times c, which is 4. And then the whole thing over 2 times 1, right, which is a. So 2 times 1, and we end up with 2 plus or minus square root of, that's 4 minus 16, which is what? -12 over 2, right? So that's 2 plus or minus, let's break 12 up into square root of -12 into 3 parts, the perfect square part, the non-perfect square part, and the -1, right? So the perfect square part is 4, the non-perfect square part is 3. If you break it up quickly, you'll see 2 gives you 6, 2 gives you 3, 3 gives you 1. There's the perfect square part, and there is the non-perfect square part. And then the whole thing over what? 2. So you end up with 2 plus or minus 2 radical 3i over 2. Now, if you break it up, you get 2 over 2 plus or minus 2 radical 3 over 2i. Of course, these 2's cancel out, so do those 2's. So we end up with x equals -1. Remember here, when they're canceling, they are leaving you 1's, and you don't just put nothing, you have to put the 1, right? So we get 1 plus or minus square root of 3i. Okay, so here are three solutions for that equation now. The one we were familiar with from an algebra class, and the two new non-real complex conjugate roots that we were not able to find when we were studying algebra only. So we get one, or algebra before learning about the set of complex numbers. Because at the end of an algebra class, we do learn about the set of complex numbers, right? 1 minus square root of 3i. Now, make sure you never write the I so that it looks like it's under the square root, okay? Because that would be incorrect. I itself, remember, is the square root, so you don't want to put it under the square root. So these are the three solutions of this equation that we used to only think has one solution. Okay, one of them is the familiar one, -2. The other two are new ones that we now know how to find because we have access to the set of complex numbers. I want to remind you that sometimes instead of writing square root of 3i, some people write I times the square root of 3, and that's okay too. So 1 plus I times square root of 3, 1 minus I times square root of 3. In case you see that, don't panic, you have the right answer, okay? And now we want to take a look at a couple of problems with more than one letter in them. These are called literal equations, or often coming from science, they're called formulas, okay? So we want to go ahead and solve this equation for t. Now the t is squared, so this is a quadratic equation in t. Remember, it would only be linear in S or G, but in t it is a quadratic equation. So let's go ahead and proceed. All right, now I'm going to first and foremost try to get rid of that fractional form so I can get a whole numbers. It's a little easier to work with. So I'm going to write that as s over 1 equals gt squared over 14. I never pass up on an opportunity to write an equation. If possible, you don't force this, but if possible, write it as a proportion so you can cross multiply. It's a very fast way to get to your answer. So here I'm going to go ahead and multiply. This cross product gives me gt squared. And this cross product gives me 14s. Remember, if a over b equals c over d, that implies AD is equal to BC. When you have two ratios that are equal, the cross products are going to be equal, right? So we get gt squared equals 14s. Now remember, we're solving for t, right? So that means we're going to isolate the t squared term here, divide both sides by g. So we get t squared equals 14s over g. When you type these into your MyMathLab or similar system, remember, you have to stick with the same case. This is capital, you have to use capital in your answer. If it's lowercase, you have to use lowercase in your answer. Now, it looks like it's possibly lowercase as well. So I usually like to put this little end here to make it not look like a 5, but when I plug it into as an answer, I'll use the right cases, okay? So now we're ready actually, because we have something of the form x squared equals k. Does that look familiar? What does the square root property tells us? What does it tell us? It tells us that x has to be plus or minus square root of k, right? So you can imagine this whole thing as being your k, sorry, right? So you end up with t equals plus or minus square root of 14s over g. Now, that is not simplified because you have a radical in the denominator, so we're going to keep going. So that means plus or minus square root of 14s over square root of g. Now we want to rationalize the denominator, so we're going to multiply top and bottom by the square root of g. So we end up with plus or minus square root of 14sg over, what is the square root of g times square root of g? Remember, the square root of any number times itself is like the square root of that number squared, which is just the number, right? So that's just going to be g. And just like that, you're done. There are your two solutions for t. If you haven't done so already, make sure that you can do this completely on your own before you move on. All right, let's solve one more of these before we move on to the next concept, which is that of the discriminant. That's going to be a short little piece, and then we're done for the day. So there is light at the end of this tunnel. I know it's a very long video. I warned you in the beginning. Usually the videos won't be this long, don't worry, but sometimes, you know, we can't help it. Okay, so notice that I'm gonna get everything on one side and try to go to ax squared plus bx plus c equals 0 form, except here my variable is t. So basically I'm aiming for at squared plus bt plus c equals 0, right? So now I have 1/2 at squared here, right? And do I see a t term in this problem? I don't. So even when I get to this form, I'm going to have a simpler scenario than what this would be. So I may not end up having to use the quadratic formula for this after all. So let's see. We get r minus r0 like that, right? Notice now we can write it like this. R minus r0 over 1 equals at squared over 2. Let's cross multiply to get at squared equals 2 times r minus r0. Again, we use cross multiplication because it's so helpful. Now, remember we're solving for t, so we go ahead and divide both sides by a, so we get t squared equals 2 times r minus r0 over a. Now we're ready to apply the square root property. So we get x squared equals k implies x equals plus or minus square root of k. So we get this implies by the square root property that t equals plus or minus square root of 2 times r minus r0 over a. But remember, we have to keep going because we want to get rid of that radical down below, right? So we split it up like this, and then we rationalize by multiplying top and bottom by square root of a, right? So we end up with the square root of, I'm going to multiply the 2 and the a, so I get 2a times r minus r0 all over a. And there is my solution for t. Okay? Similar to the previous one, so make sure you understand it before we move on. All right, for the last topic of the day, we're going to talk about the most important part of this quadratic formula. Remember, the part that's going to tell us what kind of solutions we're going to have, right? Now, the expression b squared minus 4ac, which is basically the radicand, right, in the quadratic formula, is called the discriminant because it can help us determine the nature of solutions of a quadratic equation as long as the a, b, and c are real rather than complex, and because most of the quadratic equations we're going to encounter, even though they may have complex solutions, the coefficients are usually real. And sometimes we just want to know the nature of the solutions without actually having to solve them. So that's where the discriminant comes in, okay? Now, here is the way that it's going to work out. If we take the standard form quadratic ax squared plus bx plus c equals 0, and let d, or the discriminant, be just b squared minus 4ac, the value of d is going to tell us the nature and number of solutions in the following way. If d is greater than 0, in other words, the quantity under the radical is what? Is positive, and d is a perfect square. For example, 49, right? So what's going to happen? You're going to get plus or minus square root of a perfect square, right? And that's going to give us two different solutions, but they're going to be very nice, because if we limit ourselves here, in fact, to integer values for a, b, and c, that means we're going to have two unequal rational solutions, okay? Because the plus case will give us one rational solution, and the minus case will give us another rational solution. So we end up with two unequal rational solutions. Now, this is the nicest kind of quadratic equation. It's the kind, when this happens, you know for a fact that this part here would have been factorable over the set of integers had we tried it, okay? Now, the other scenario is when d is positive, in other words, the discriminant is positive, but it's not a perfect square. We're still going to get two real solutions, but they're going to be unequal irrational solutions, okay? And these would not have been, this kind of equation would not have been factorable over the set of integers. The other scenario is if d is 0, right? If d is 0, that means this part is gone. So you just get what? Negative b over 2a as the only solution. So you get one rational, because it appears as a solution twice, one from the plus case, one from the minus case, but it's the same solution. We say it's one rational double solution. It's the same solution occurring twice. And if d is negative, that means we're going to have a square root of a negative number, which is going to end up giving us what? Two complex conjugate solutions. And in fact, they're not just complex, but they're non-real complex conjugate solution, okay? Solutions. All right, so these are the possibilities. Positive perfect square would give us two unequal rational solutions. Positive and not a perfect square, we get two unequal irrational solutions. 0 will give us one rational double solution, or double root. Solutions are also called roots. And the negative will give us two non-real complex conjugate solutions. All right, let's take a look at some examples and then call it the day. All right, so remember, we want to find the number and types of solutions of each of these without solving them. So that means we need what? We need d. So here we know that a is 2, b is 3, and c is 1. So we know that capital D, which is the discriminant, is b squared minus 4ac. So it's going to be 3 squared minus 4 times 2 times 1, right? So that's going to be 9 minus 8, which is 1. Notice d is greater than 0 and d is a perfect square. So what does that category tell us? That means we're going to have what? That we're going to have two unequal rational solutions, right? And would it be factorable over z? The answer for part, so for part A, the first part, it's this. For the second part, the answer is what? Yes, it would have been factorable over the set of integers. And in fact, if you try it, you can easily factor that, right? So you have 2x and x, 1 and 1 will do it. So 2x plus 1 times x plus 1 equals 0. See? So that means it was factorable, and you can verify that very quickly. For the next one, remember, before you can find the discriminant, you have to put it in the right form, right? So we're going to distribute x squared minus 10x, move the negative 7 over, so plus 7 equals 0. So now we have a is 1, b is negative 10, and c is 7, right? So the discriminant is b squared minus 4ac. So it's going to be negative 10, quantity negative 10 squared minus 4 times 1 times 7. So we're going to have 100 minus 28, which is 72, right? So notice d is greater than 0, but d is not a perfect square. So therefore, two unequal irrational solutions. And is it factorable over the set of integers? No. Okay? How about this one? Well, you could find the discriminant as is, or better yet, get rid of the fractions, then find the discriminant, because getting rid of the fractions isn't going to change the solutions, okay? So let's do that. Of course, this should look familiar to you. We've done this problem earlier in the lecture. So the LCD was 12, if you remember. We're going to multiply all both sides by 12, so that means all terms because of distribution, right? So 12 times, and then times 12 times 12 times 12. So we end up with 6x squared plus 4x plus 3 equals 0. So a is 6, b is 4, c is 3. So the capital D, which is the discriminant, is going to be just the b squared minus 4ac part of the quadratic formula. So it's going to be 4 squared minus 4 times 6, which is a, times 3. So we're going to have 16 minus 24 times 3, 72, right? Do I even need to go further? No, not really, because all I know is that this is less than 0. That's all I need to know. D is less than 0, so therefore we're going to have two unequal, non-real, complex conjugate solutions, okay? And of course, these won't be factorable over the set of integers. All right, last one. So we have, it's already in the right format, so we're ready. A is 1, B is negative 6, and C is 9. So capital D, which is the discriminant, is going to be B squared minus 4AC, which is going to be quantity negative 6 squared minus 4 times 1 times 9, which is 36 minus 36, which is 0. So when it's 0, that means the part under the radical is gone, so we're just going to have one real double solution. And it'll be rational. So one rational double solution, or double root, okay? And yes, this will be factorable. In fact, x squared minus 6x plus 9 equals 0 can easily be factored as x minus 3 times x minus 3 equals 0. So you get x minus 3 equals 0, or x minus 3 equals 0. So x equals 3 or x equals 3. You see why we call it a double root or double solution? Because you get 3 as a solution twice if you actually try to solve it, okay? All right, so I know that was a long video, and I apologize, but that's life sometimes. So we wanted to learn as much as we could about quadratic equations, and hopefully we did, right? So that should do it for this video. So you take care, and we'll see you next time.